Okay, so just now we do know that if I have the, okay, we measure, let's say for example, rate of reaction. Of catalyst. Okay, so if I plot the graph, so T, this is the concentrations of volume of O2. Okay, release. So in this case, cm3. T, let's say per second, for example. Okay, so we start to measure. Okay, then get this. So what we're going to do here is we always can place, is because this time equal to 0. So we always can place our gradient. Okay, the tangent, sorry, and then we draw the grade. Okay, we can calculate the gradient. So this one is called dp. This one is dt. So the rate is equal to the gradient. So equal to the dp over dt. So this one no problem, because at the end, let's say for example, so dp equal to 20 cm3, t equal to 10 seconds, for example. Okay, so therefore rate will equal to dp 20 over 10, so equal to 2 cm3 per second. Okay, so you will calculate, correct or not? Okay, generally very simple. In this case, you can see that my rate of reactions or initial rate of reactions, okay, equal to, sorry, let me get my pointer. Okay, can you see that the rate actually will equal to 20 over 10, so 20 cm3 over 10 seconds. So initial rate of reaction is very high. Every second, can you see that, guys? Every second give us 2 cm3 of the O2. Are you clear? Okay, but this only tell me the initial rate of reactions, but I do not know when the reaction actually stop. Clear or not? So I can calculate. This is initial. Okay, sorry, I put it initial rate of reactions. Okay. If I want to know what is the overall rate of reactions, then what we're going to do here is we check where is the point where you get a plateau. Let's say, for example, here. Okay, let's say 20 seconds. Let's say, okay, and then here, let's say 30. Okay, I mean, I just make up this value. So overall rate of reaction also equal to dp over dt. But now dp here we take overall. Okay, overall so 30. dt overall here 20. So you get 1.5 cm3 per second. Are you clear? Means the overall rate of reaction generally will be lower compared to initial rate of reaction. Because why? Because the gradient's always, okay, decreasing. Can I see that? The gradient, highest near to 0, but slowly decrease until we get the 0. So this part we cannot consider because no reaction already, right? No reaction already. So we cannot actually claim that this part continue because no reaction already, stop already. Are you clear? So it stopped may due to many reasons. One of the reason here, why it stopped? Why it stopped here? One of the reason, okay, substrate concentration now equal to 0. Why equal to 0? Because used up or completely reacted. So or no more substrate already. So that's why you cannot actually continue. If you continue, then the overall rate of reaction will be different. People will have different rate of reactions already. Why? Because you continue. You take how long? If I take 1 hour, then your rate of reaction will be even worse. Correct or not? So you have to check at a point where you immediately turn into the plateau. Then I can get the overall rate of reactions. Okay. Now, let us look at another one. Just now we learned about this rate of reactions that can actually calculate that from the graph where the disappearance of the substrate actually take place. Okay, so now look at this. This is the color intensity. Versus the time. Okay, so color intensity in this case, let's say in terms of percent. Okay, or okay, don't use percent. I mean, normally we absorbent we use percent. Color intensity normally we use how many units? Arbitrary units. Okay, AU, and time, let's say second. Okay, so now what we're going to do here is when you measure here, so you plot the graph, you use colorimeter to determine the color intensity or absorbance here, then we can get a graph. Okay, this is what we have plotted just now. Okay, now this kind of graph, if you calculate, okay, initial rate of reaction, then you realize that your initial rate of reaction actually meaningless. Okay, so let's say I put my tangents here. Then I can get this. Okay, the gradient. Cannot my initial rate of reaction. Okay, but now you realize something is, if I plot this, let's say this one give me 0.5 unit, 0.5 is too big to, okay, this highest, let's say 3.0 unit. And here is in, let's say 10 seconds, for example. Okay. So what will happen here is, if you calculate initial rate, so you can see that actually against is the dy over dt, right? Not okay, the color intensity. Okay, so it's not product, guys. This is not product. Color intensity, we cannot say dp already. So in this case, I say y equal to color intensity. So I put dy over dt. So dy equal to 3.0 and it's negative. Okay, we change to positive in this case. Okay, and then 10 seconds. So in this case, get 0.3 arbitrary units over 10 seconds. Now, what will happen here is this is not a true rate. What you measure here, can I see that? This is not a true rate. Why is it not true rate? Because what you measure here is the color intensity. Is how fast color intensity change. Correct or not? How fast color intensity change? Okay, yeah, every second 0.3 units. But is it a true rate? It's not a true rate, because the true rate, it should be how fast starch disappear. Are you clear? You get what I mean here or not? So initial rate of reaction here, it can be 0.3 is how fast the color actually decolorize or color change. So in this case, every second we have 0.3 units of color change. So initial rate is not a true rate. So in order to get a true rate for this kind of reactions, then we only can go for, we get the true rate of the reactions, then we only can go for what we call the overall rate of reaction. So how we calculate overall rate of reaction? So in this case, you get where they reach the plateau. Let's say in this case, 100 seconds, for example, let's say 20 seconds, for example. Okay, 20 seconds. So if you get the overall rate of reactions for this kind of graph, overall rate of reaction actually equal. Now in our syllabus is equal, yeah, 1 over T. The formula is 1 over T. T is basically the time when reactions is stopped. T is the time when reactions stop. So it means that if you look at this, so let's say this part reaction stop already at 20. This one not really reaction stop here. Okay, let me change a bit. So let's say I think somewhere here. Okay, so let's say 50 seconds. Okay, so means that in this case we're equal to 1 over 50. So calculator, help me to calculate. 1 over 50 is 0.02. Am I right? Okay, so answer is 0.02 per second. So this is the overall rate of reactions, how we calculate. Now, in fact, this one is because our syllabus say that it's 1. So sometimes question may tell you 120. So you just use the value that they give. Do you get what I mean here, guys? Okay, so because in the rate of reactions here, we assume that the rate constant is equal to 1. So in fact, the correct ones actually overall rate of reaction is proportional to 1 over T. So means that the overall rate of reactions when equal to K over T, where K is a rate constant. So in our syllabus, we make the K constant or rate constant equal to 1 in our syllabus. So therefore, now our overall rate is 1 over T. So this is a true rate, okay, of the reactions. So far, clear or not? Okay, so let us look at another reaction. This reaction actually is the hydrolysis of triglycerides. So lipase. So the hydrolysis of triglycerides will give us glycerol plus 3 fatty acid. Okay. So now, if I measure the pH, the change in pH, what do you expect to see? Right? So we expect that, okay, the pH will drop because of the fatty acid. So fatty acid actually release the proton. So therefore, you can see that the pH drop. But if I measure the initial rate of reactions where equal to 0.2 per second, this one is show how fast the pH drop. It doesn't show us the direct measurement. So it's no direct measurements, then I will go for the overall rate of reactions, which is 1 over T. 1 actually is a rate constant here. So 1 over 50 seconds, where with the time the enzyme stop the reactions. Correct or not? Okay, so it gets this value. But the question here is where this is become constant already, the plateau already, we know that as enzymatic reaction stop. But can I claim that's completed or not? Okay, so we have no enough data to say that the process is completed, because it might, okay, yes, it might be substrate used up already. So all triglycerides, okay? So it means that hydrolysis process completed. It might be. Are you clear? But now we also have a one curious here, okay? Why? Because there is a drop of pH. So it means that from optimum pH to the pH that actually not suitable for the enzyme. So it means that the pH drop may actually cause the denaturation of enzyme, the lipase. So therefore reaction stops. So which one we do not know. Are you clear? So the only way to know this, then we have to check whether still got triglyceride or not lah. After 50 seconds, I test for triglyceride. I take some sample and check for triglyceride, whether triglyceride is there or not. Definitely, it's not easy to measure the triglyceride because colorless. So how we view it, we have to use the instruments, okay, to check whether triglyceride is there or not. If there's no triglycerides, then yes, hydrolysis is completed. If triglyceride is still there, then our what we call this the conclusions or the explanation might be because the pH dropped, therefore cause the enzyme to be denatured, and then enzyme no longer can function. That's why reaction actually stop. I wouldn't say completed. You can see that whatever I wouldn't say the the reaction completed. I say reaction stop. Stop due to what? It might be because of hydrolysis completed. It might be also, it might be because of the pH and the decrease of the pH. Are you clear? Okay, guys, so far clear or not? Okay, so I give you the final example here before we go for our practical slots. Okay, now, if my graph is this thing, is this one. Mass of starch, milligram. Okay, this is time, T in second. So again, you get this drop. So if the question asks you to calculate the rate of reaction, so can I go for initial rate of reaction or not? Okay, answer my question now. So we can always calculate the rate of reactions, okay, based on this, because our initial rate of reactions give us the idea how fast the substrate disappear. So in this case, per second, I can actually know that negative 20 milligram of starch is hydrolyzed. If we compare to just now, what we have, let's say in this case, every second, my intensity drops 0.3. I do not know what it means by 0.3. I cannot imagine, I cannot actually figure out how fast the substrate actually disappear. But now with this, I know that's, okay, I know that's how fast, because every second I have 20 milligrams of the substrate being hydrolyzed. Okay,